NASA quietly altered the trajectory data for the interstellar object 3I Atlas. No press release, no explanation, just a silent revision that shifts its predicted path away from Jupiter's Hill sphere. And that change has triggered new questions about the object's physics. A non-gravitational acceleration, too strong for its measured mass loss, X-shaped outgassing jets, unlike any known comet, and radio emissions sitting precisely at the waterhole frequencies that match the direction of the 1977 WOW signal. All of this lands just as the UN prepares for an unprecedented planetary defense drill on December 19th. In this episode, we'll break down what NASA changed and what the new data suggests about Atlas itself. If clear, evidence-driven analysis helps you follow discoveries like this, consider liking and subscribing. Let's begin. To understand why that update matters, we need to look directly at the numbers NASA changed. Within about 48 hours of a Harvard professor pointing out what he saw as an unlikely coincidence, the Jet Propulsion Laboratory updated their model for the non-gravitational acceleration of the interstellar object called 3I Atlas. The key parameter that tells us how much 3I Atlas deviates from a purely gravitational path was reduced by roughly a factor of 6, from approximately 1.66 times 10 to the power of -6 astronomical units per day squared, down to about 6.8 times 10 to the power of -7 astronomical units per day squared. On paper, the change happened almost overnight, as the team switched from a model based on water ice physics to a model based on carbon dioxide ice physics. That change also shifted the predicted path of the object. In the earlier version, 3I Atlas was calculated to pass almost exactly at the edge of Jupiter's main zone of gravitational control, a region known as the Hill radius. In the revised version, the closest approach is moved just outside that boundary. One model placed the object right at Jupiter's gravitational doorstep. The other puts it just beyond. The open question is whether this is a simple correction based on better data, or whether the timing hints at something more complicated inside the modeling process. The first sign that anything unusual was happening came in the final days of November 2025. Independent researchers who watch updates to the Jet Propulsion Laboratory Horizons database noticed that the numbers for 3I Atlas had shifted. These were not tiny tweaks within the normal uncertainties. The core non-gravitational parameter, the one that encodes how much extra push the object feels besides gravity from the sun and planets, had changed by that factor of about 6. The timing matters because, just days before this change, Avi Loeb at Harvard had released an analysis of the original data. His work pointed out that, under the earlier Jet Propulsion Laboratory solution, 3I Atlas was predicted to reach its closest approach to Jupiter on March 16, 2026, at a distance that almost perfectly matched Jupiter's Hill radius. The Hill radius is the distance around a planet where its gravity dominates over the gravity of the Sun, so objects near that boundary can, under the right conditions, be captured into orbit. Loeb estimated that the odds of an interstellar object naturally passing that close to Jupiter's Hill radius were less than 4 in 100,000. That is not impossible, but it is rare enough to demand attention. Loeb sent his analysis by email to David Diania, a navigation engineer at the Jet Propulsion Laboratory who helps maintain the trajectory data for 3I Atlas. According to the public story, there was no written reply. However, within a couple of days, the model published by the Jet Propulsion Laboratory changed. The new version adopted a different functional form for the non-gravitational acceleration. Instead of following a steeper dependence on distance from the Sun that is traditionally used for water ice-driven comets, it used an inverse square law with distance. In simple terms, the extra push on the object now falls off as 1 divided by the distance squared as it moves away from the Sun. An inverse square dependence is what you would expect if the acceleration is mainly driven by carbon dioxide ice sublimating or turning directly from solid into gas as the object warms in sunlight. Water ice and carbon dioxide ice begin to sublimate at different temperatures and at different rates, and they create different patterns of non-gravitational acceleration as a comet or comet-like body moves through the inner solar system. The natural question is which description fits 3I Atlas best. A major clue comes from observations with the James Webb Space Telescope in August 2025. A team led by Martin Cordner measured the composition of the gas in the coma of 3I Atlas, the fuzzy cloud around the solid core. Their analysis showed that this interstellar object is unusually rich in carbon dioxide. The ratio of carbon dioxide to water in the gas was about 7.6 to 1, with an uncertainty of plus or minus 0.3. Among known comets, that level of carbon dioxide dominance sits near the extreme high end. So at first glance, a carbon dioxide-based model looks well supported, yet the way the object brightened as it moved toward its closest distance to the Sun tells a different story. Observations during September and October 2025 recorded the changing brightness of 3I Atlas as it moved inward toward perihelion. The total light output grew very quickly, following an approximate power law where brightness increased as the inverse of distance raised to the power of about 7.5. That is far steeper than the inverse square behavior assumed in the updated Jet Propulsion Laboratory model. A simple carbon dioxide-driven comet would not normally brighten that rapidly with distance. Such a steep dependence suggests that near perihelion, something unusual was happening. The object was not just warming at a steady rate and venting gas in a smooth pattern. Instead, the outgassing was being amplified in a much sharper way. When you feed that steeper radial dependence into the trajectory calculations, the predicted closest approach to Jupiter moves back toward the Hill radius value. The coincidence with Jupiter's gravitational boundary reappears. The important question is not whether the Jet Propulsion Laboratory team made a mistake. Updating trajectories with new data is standard practice in planetary science. When better measurements become available, models should change. The deeper question is whether the current model truly captures the physics of what 3I Atlas is doing. On this point, the information we have pulls in different directions. The light curve argues that the non-gravitational acceleration near perihelion must have been stronger and more sharply peaked with distance than the new model allows. The composition data argues that carbon dioxide is the main volatile driving activity. The trajectory revision moves the predicted passage from right at Jupiter's Hill radius to just beyond it, and the timing of the change, coming soon after a well-known scientist drew attention to the original coincidence, raises questions that cannot be answered by equations alone. What we do know with high confidence is that the non-gravitational acceleration itself is real. The detection stands at about 10 standard deviations of statistical significance. In the language of astronomy, that is a very strong result. 3I Atlas is not moving on a path controlled only by gravity. There is an extra force acting on it. For a natural comet, that extra push should be easy to explain. As sunlight warms the surface, ices sublimate and gas streams away. The escaping gas carries momentum, and by Newton's third law, the nucleus is pushed in the opposite direction. This rocket-like effect has been seen in many comets and is described by well-tested physics. If 3I Atlas were behaving like a typical comet, the numbers would fit that picture. Instead, the acceleration seen near perihelion implies something much more dramatic. Applying the laws of momentum conservation, researchers find that 3I Atlas would have had to shed at least 10 to 15% of its total mass in only a few weeks. Given a minimum mass estimate of about 33 billion metric tons, that implies billions of tons of material should have been ejected into space. That material would not be invisible. It would form a large cloud of gas and dust around the nucleus and trailing behind it, shaped by solar radiation pressure into a classic cometary tail. Images from early November tell a different story. After perihelion, when 3I Atlas emerged from behind the Sun as seen from Earth, observers turned their telescopes toward it. Professional projects and amateur astronomers collected image after image. Across this range of observations, one thing was consistently missing. There was no clear, bright tail pointing away from the Sun. Instead, the images revealed a more complicated structure. 3I Atlas showed a web of narrow jets, some aimed roughly toward the Sun, some away from it, and some off to the side. Analysts could identify several distinct features extending hundreds of thousands of kilometers in different directions. That is not what we usually see in a comet. Normal comets show a bright head and a single dominant tail sweeping away from the Sun, in line with standard comet physics. 3I Atlas presents a fragmented, multi-jet structure that does not fit that simple picture. There are natural ways to produce complex jet patterns. Comet nuclei are irregular. Their surfaces can have regions with different mixtures of ices and dust. As the nucleus rotates, sunlight strikes different areas and can switch jets on and off. We have seen solar system comets with distinct jets before, but something about the geometry of the 3I Atlas jets seems hard to fit into the usual explanations. Their directions, their narrowness, and how they relate to the rotation period of the object hint at a mechanism we do not yet fully understand. That uncertainty leads back to the question of modeling. If the jets are not just the straightforward result of carbon dioxide and water ices sublimating under sunlight, if some other process is shaping the outgassing, then a simple carbon dioxide-based law for the non-gravitational acceleration may leave out something important about the nature of 3I Atlas. Under the revised trajectory solution, the predicted closest approach to Jupiter is about 53.587 million kilometers, with an uncertainty of roughly plus or minus 45,000 kilometers. That places 3I Atlas slightly beyond Jupiter's Hill radius, just outside the region where we would expect objects or fragments released near perihelion to remain bound to the giant planet. It is a delicate boundary. A small change in the assumed physics can shift the outcome from likely capture to likely escape. This sensitivity is a hallmark of orbital mechanics. Change the model, and you change the predicted path. The steep brightness evolution of 3I Atlas suggests that the current model might need to be refined again. For now, we are watching a scientific process unfold in real time, with researchers across the world checking each other's work and challenging each other's assumptions. Whatever the final answer turns out to be, the story of 3I Atlas is being written in the open, one new observation at a time and one model revision at a time. What happens next will depend on the data that arrives over the coming weeks. The International Asteroid Warning Network has now begun a focused observing campaign, with telescopes across the globe contributing fresh measurements of 3I Atlas. The Hubble Space Telescope and the James Webb Space Telescope are scheduled to observe 3I Atlas again near its closest approach to Earth on December 19, 2025. Each new data point will either strengthen the current model of its motion or force scientists to alter that model once more. The strange match between the original trajectory and Jupiter's Hill radius may turn out to be only that, a coincidence produced by the geometry of orbits in our solar system. It could be nothing more than a neat pattern that shows up when you draw enough curves in three-dimensional space, or It could be the first faint sign of something we are not yet ready to accept, a hint that would challenge our standard picture of what arrives from the dark space between the stars. Whatever the outcome, the strange jets and changing brightness of 3I Atlas will be tested against these new observations. To see why this possible coincidence matters, we need to look at Jupiter. Jupiter is the largest planet in our system, and its gravity shapes the paths of many smaller bodies. Astronomers describe the region where Jupiter's gravity dominates over the Sun's gravity as its Hill sphere, and the distance from the planet's center to this border as the Hill radius. For Jupiter, the Hill radius is about 53 million kilometers. Inside this boundary, moons and occasional temporary visitors can be trapped. The 4 large Galilean moons and many smaller moons all orbit well within this zone, along with occasional temporary visitors. The Hill sphere is a thin transition region where Jupiter's pull and the Sun's pull balance. It is not a solid surface, but an invisible border drawn by gravity. What made the first 3I Atlas trajectory solution so striking is how closely it seemed to touch that shell. When you follow its path forward from perihelion, including the non-gravitational acceleration measured near the Sun, the object is predicted to reach its closest point to Jupiter around March 16, 2026. In the original Jet Propulsion Laboratory solution, that closest approach distance matched Jupiter's Hill radius within the quoted uncertainty. It was not simply somewhere inside the Hill sphere and not simply somewhere outside. It sat right at the edge. At that boundary, an object could release smaller pieces that would fall under Jupiter's control while the main body continues on its way. The fragments would be captured and could settle into orbits around Jupiter or its moons. This geometric possibility drew the attention of independent analysts. Steve Fairfax, one of the early outside researchers studying the Jet Propulsion Laboratory tables, noticed this pattern and brought it to Avi Loeb's attention. In the technical listings, the minimum distance to Jupiter was given as about 53.08 million kilometers, with an uncertainty of roughly 60,000 kilometers. Calculations of Jupiter's Hill radius at that time in its orbit yielded a value of about 53.1 million kilometers. Within the uncertainty, these numbers matched. From a probability point of view, that is a tight alignment of numbers. The Hill radius marks a thin spherical shell in space, a boundary layer, perhaps a few 100,000 kilometers thick, where the gravitational balance shifts from the Sun to Jupiter. By comparison, the volume inside Jupiter's orbit is vast. The chance that a random interstellar object would, by accident, thread that narrow shell is tiny. Loeb's estimate placed the odds at less than 4 in 100,000, a very small number. Other workers who examined the geometry arrived at similar figures. It is not the kind of match most scientists are willing to ignore without looking more closely. The flight of 3I Atlas through the inner solar system adds more context. The object did not drift in slowly. It entered from interstellar space at a speed of more than 250,000 kilometers per hour. It passed Mars at roughly 29 million kilometers on October 3rd. It then reached perihelion on October 29th at about 203 million kilometers from the Sun. During this close solar passage, astronomers measured the non-gravitational acceleration we discussed earlier. Now 3I Atlas is heading back outward toward a Jupiter encounter in March. The timing of the non-gravitational acceleration is important. The extra push peaked near perihelion, exactly when a normal comet would shine most brightly and vent gas most strongly. As sunlight grows more intense, ices warm, turn to gas, and stream away. From an orbital mechanics standpoint, perihelion is the ideal place to adjust a trajectory. This ties into the Oberth effect, named after rocket engineer Hermann Oberth, which describes how a spacecraft can gain or lose energy most efficiently when it uses its engines at its highest speed deep in a gravitational field. At perihelion, 3I Atlas was traveling at roughly 68 kilometers per second. Any thrust applied at that point, whether it comes from natural outgassing or from some other process, has a large effect on the eventual orbit. A tiny change in speed at such a high velocity becomes a noticeable shift months later. In this case, the measured non-gravitational acceleration is on the order of 0.02 millimeters per second squared. It is far weaker than Earth's gravity or the Sun's pull at that distance. Yet when such an acceleration acts for many days near perihelion, it can move the path by a meaningful amount. Calculations show that an effect of this size, applied over the observed time, is enough to alter the predicted Jupiter encounter distance by roughly 100,000 kilometers, just the amount needed to bring the original solution into line with the Hill radius. It is important to separate pattern from proof in our thinking. Explaining how a small push near perihelion can fine-tune a later encounter is not the same as claiming that anyone aimed the object at Jupiter. The straightforward interpretation is that 3I Atlas is a comet-like body responding to solar heating. Gas escapes, momentum is carried away, and the trajectory shifts according to the laws of physics. Under this view, the close match to Jupiter's Hill radius is a coincidence. The more speculative idea is that 3I Atlas is not purely natural, and that its trajectory was shaped with intention. In that picture, the perihelion passage would have been used to refine an approach to Jupiter's gravitational boundary for some unknown purpose. The present dataset can be made to fit both broad stories, so the situation remains unresolved. If the Hill radius match were deliberate, the geometry would make a certain practical sense. An object that passes exactly at the Hill radius can release smaller units that have slightly lower speeds relative to Jupiter. Those smaller units would then fall inward and be captured. From there, they could perform any functions they were designed for, such as observing or listening. Jupiter has been a major feature in our system for roughly 4.5 billion years. Any technologically capable society elsewhere in the Milky Way, with a clear line of sight to our region, could, in principle, detect Jupiter through its gravitational effects or its reflected light. They could estimate its mass and infer that it dominates the architecture of our planetary family. If such a group wanted to study our solar system from a distance, targeting Jupiter would be a logical choice. It is massive, bright, and surrounded by many moons. It also sits far enough from the Sun that an orbiter near it would enjoy a relatively stable environment with a wide view inward. These ideas are speculative, but they are rooted in basic physics and in how observers might plan a long-term survey of a distant planetary system. The model revision made by the Jet Propulsion Laboratory complicates this picture but does not erase it. By switching to a carbon dioxide-driven inverse square law for the non-gravitational acceleration, the new solution moves the closest approach distance to about 53.587 million kilometers, with an uncertainty of around 45,000 kilometers. That is roughly 500,000 kilometers outside the nominal Hill radius. Close, but no longer a near-perfect match. At first glance, that shift seems to weaken the idea that the Hill radius has special significance. If the object appears to miss that boundary by several 100,000 kilometers, then the earlier alignment might simply have been an artifact of incomplete data. Yet the way 3I Atlas brightened near perihelion does not sit comfortably with a simple inverse square dependence on solar distance. Observations suggest a much steeper relation, closer to distance raised to the power of -7.5. If the true non-gravitational acceleration followed something like that steeper law, the resulting trajectory prediction would differ from the current model, and the Hill radius match could reappear. Right now, the answer depends on which functional form best tracks reality, and that question is still open. As new measurements are added to the orbit solutions, the predicted path of 3I Atlas will continue to shift until we have a long, precise record of its motion. The issue of whether it is aimed at Jupiter's gravitational boundary will remain unsettled. This is a moving target, both on the sky and in our calculations. There is also a practical angle to the Jupiter encounter. Jupiter is currently being studied by NASA's Juno spacecraft, which has been in orbit since 2016. When 3I Atlas makes its closest approach in March 2026, Juno will be at a distance of roughly 53 million kilometers from the interstellar object, comparable to the Hill radius itself. That separation is large in human terms, but modest in planetary terms. It is close enough that, in principle, Juno could detect certain kinds of disturbances or signals if they exist. Juno carries a radio and plasma wave instrument that measures electric and magnetic fluctuations over frequencies from tens of hertz up to many megahertz. If 3I Atlas emits radio noise or structured signals within that band, Juno could, by chance, record them. The spacecraft was not designed for that purpose, but many discoveries in space science have come from instruments being used in ways no one fully planned at launch. The European Space Agency's JUICE mission is also on its way toward the Jupiter system. JUICE will be farther from 3I Atlas during the March encounter than some Mars orbiters were earlier, but it will observe the system in a different state. By then, 3I Atlas will be well past perihelion and may still be active. For now, the scientific community waits, observes, and keeps refining models. The cautious, skeptical position is clear enough. Random processes sometimes line up in surprising ways, and human beings are excellent at spotting patterns, even in noise. If 3I Atlas were predicted to pass at some ordinary distance from Jupiter, nobody would likely be discussing it. The fact that we notice this specific alignment may say as much about our pattern-seeking minds as about the object itself. The alternative view is more controversial. It points out that the trajectory of 3I Atlas seems to contain several unusual features, from its alignment with the plane of the solar system to its close approaches to other planets and the timing of the solar conjunction that hid it from Earth. When several low-probability elements appear in one story, it is reasonable to ask whether pure chance is still the best explanation, or whether something deeper is at work. At this stage, neither interpretation can be proven or ruled out. That is the honest scientific assessment. The current data can be fit into a natural comet framework and into more speculative frameworks. As more observations arrive from Earth-based telescopes, from Hubble and James Webb, and eventually from spacecraft in the Jupiter system, some ideas will gain support and others will fade. Until that happens, the question of what the Jupiter coincidence truly means will remain open. What we can do, while we wait for more data, is outline the kinds of observations that could separate the different possibilities in front of us. If 3I Atlas releases smaller objects as it passes Jupiter, and those fragments move into Jupiter's Hill sphere and settle into stable orbits, that would count as strong evidence against a purely natural explanation. On the other hand, if the jets and outgassing behave as standard comet physics predicts, with no anomalies beyond what an unusual mixture of ices can explain, that would support the view that 3I Atlas is a strange but natural interstellar comet. The next few months will be crucial. The International Asteroid Warning Network Observing Campaign continues through January 2026. The close approach to Earth on December 19, 2025, will give us the best observing conditions we are likely to have for this object. Telescopes on the ground and in space will measure its position, brightness, spectrum, and structure with high precision. The encounter with Jupiter in March 2026 will then either support the skeptical view in which all of this is an unlikely but natural coincidence, or it will force a deep rethinking of what we believe about visitors from interstellar space. While we wait, the jets from 3I Atlas continue to surprise astronomers. Observers have identified 7 distinct features pointing in directions that are difficult to reconcile, with a rotating nucleus obeying standard comet physics. The details of these jets may hold the key to everything else, because if the jets are not what they first appear to be, then 3I Atlas itself may not be what we assume. On the morning of November 8th, 2025, at about 4:10 Coordinated Universal Time, 3 astronomers in Europe recorded something unusual. Michael Jager, Gerald Riemann, and Enrico Prosperi pointed their telescopes at the region of sky where 3I Atlas had just reappeared from behind the Sun after solar conjunction. They combined 24 green filter exposures, each lasting about 35 seconds, along with additional frames taken in red and blue filters. When they stacked and processed the images, they saw a structure that shifted the conversation about this interstellar visitor. The processed images revealed a bright coma, a halo of gas and dust extending outward to nearly 500,000 kilometers from the nucleus. Many active comets grow large comae as they shed material, so that by itself was not the surprise. What drew immediate attention were the narrow features embedded in the halo. At least 7 distinct jets were visible. Some pointed roughly toward the Sun, some roughly away from it, and some stretched off in directions that seemed to have no clear connection to the pattern of solar illumination. To see why this is strange, it helps to recall how comets normally behave. A comet nucleus is a mixture of rock, dust, and various ices. As a comet approaches the Sun, solar radiation warms its surface. Different types of ice, such as water ice, carbon dioxide ice, and carbon monoxide ice, begin to sublimate, turning directly from solid to gas. This gas flows away from the surface at speeds of a few hundred meters per second, roughly 300 to 400 meters per second for typical temperatures. It drags dust particles with it, lifting them off the surface and creating the fuzzy glow of the coma. The escaping gas also exerts a tiny push on the nucleus. For every molecule that flies off in one direction, the nucleus experiences a small push in the opposite direction. When you add up the momentum carried away by billions of molecules each second, you get a measurable, non-gravitational acceleration, which astronomers can detect and model. There is a simple geometric expectation built into this process. Ice sublimates where it is heated. The Sun is the source of that heat. Therefore, the strongest outgassing should occur on the side of the nucleus facing the Sun, where sunlight is most intense. The jets should generally point toward the Sun, or at angles that can be explained by the way sunlight falls on the rotating surface. When we look at well-studied comets in our own solar system, this is what we usually see. Jets roughly aligned with the sunward side, and a dust tail swept away from the Sun by radiation pressure. 3I Atlas does not follow that pattern. The November 8th images revealed jets pointing in several directions, including some that are nearly opposite to what a basic illumination model would suggest. Images taken on November 9th by Frank Nebling and Michael Jager showed even more complex structure. 2 so-called anti-tail jets appeared to extend roughly toward the Sun for distances approaching 1 million kilometers. At the same time, a longer, tightly collimated jet extended away from the Sun for almost 3 million kilometers. On the sky, the longest of these features covered an angle of about 30 arc minutes, roughly the apparent diameter of the full moon. These are not marginal details at the edge of detectability. They are enormous structures spanning millions of kilometers of space, clearly visible in stacked images and confirmed by more than one observing team. According to standard comet physics, structures of this size and shape, pointing in these directions, should be rare and short-lived. The complication comes from the fact that 3I Atlas is rotating. During July and August of 2025, before it went behind the Sun, astronomers measured small changes in its brightness and inferred a rotation period of about 16.16 hours. This is an ordinary spin period for a cometary nucleus. The problem arises when you think through what rotation should do to the jets. If a jet is produced by a specific active region on the surface, then that region moves as the nucleus rotates. Over a full rotation, the active spot faces toward the Sun, then toward the night side, then back again. A jet that is strongest when the spot is sunlit and weakest when it is in darkness should turn on and off with this cycle. Gas leaving the nucleus at a typical speed of around 400 meters per second travels tens of thousands of kilometers during each full spin, on the order of 23,000 kilometers. If the jet is pulsing on and off as the nucleus rotates, the material it releases should form a series of separate segments along its path. One researcher has described this expected structure as resembling peas in a pod, with each pea marking material emitted during one period of illumination, and the gap between them marking the time when the source region was turned away from the Sun. In such a case, the jets would not be smooth, continuous lines. The November images of 3I Atlas do not display that pattern. The jets are continuous. They extend smoothly outward for millions of kilometers with no obvious breaks or repeating gaps that match a 16-hour period. Their shapes suggest a flow that has been steady over timescales longer than the rotation period, and their directions remain tightly collimated, meaning that they stay narrow and well-aligned instead of spreading out. One natural explanation involves the orientation of the rotation axis. If the spin axis happens to point roughly toward the Sun or roughly away from it, then one polar region on the surface would remain in nearly constant sunlight, and the opposite polar region would remain in nearly constant shadow. Ice near such a sunlit pole could sublimate continuously without being switched on and off by rotation. Jets emerging from these polar regions would then remain active and stable in direction. This explanation is workable, but it requires that the rotation axis be aligned in a fairly specific way, so it adds another coincidence to the list. Another possible explanation focuses on the surface topography of the nucleus. Imagine ice deposits lying at the bottoms of deep valleys or craters, surrounded by high walls. Sunlight would only reach these deposits when the Sun is at certain angles and when the nucleus is rotated just right. In that case, the jets might be highly localized and point in unusual directions defined by the shape of the terrain. This idea can explain why some jets point along specific paths, but it still tends to produce on and off behavior as the nucleus rotates. The observed jets from 3I Atlas, however, show a smoother, more constant structure than this simple shadowing model would suggest. A third natural hypothesis is that the features we see in the images are not active jets anchored to the surface at all, but instead are the trails of fragments that broke away from the main nucleus during perihelion. Each fragment would then act like a small comet, leaving its own trail of gas and dust as its ices sublimate. The straight, narrow lines could trace the paths of these fragments, moving away on slightly different trajectories. This fragmentation idea has some support in the data. The linear features extend in multiple directions, consistent with fragments flying off in different paths. However, later observations complicate this story. Images taken on November 11th by observers such as David Jewett and Jane Liu show what appears to be a single dominant nucleus rather than multiple bright cores. If 3I Atlas had broken into many large pieces at perihelion, we might expect to see several bright condensations instead of one main source. The apparent lack of multiple nuclei suggests that, if fragmentation occurred, it either produced many small, faint pieces or happened in a more limited way than the simple picture of major breakup would imply. The antitail features are another challenge. An antitail is a structure that seems to point toward the sun instead of away from it. Standard comets sometimes show apparent antitails due to perspective. When we view a dust tail edge on, it can look like a spike pointing sunward, even though the dust is actually streaming away from the sun. In the case of 3I Atlas after perihelion, the viewing geometry from Earth was not edge-on in that way. The jets that appear to point toward the sun seem to be physically real features, not just illusions of perspective. If these structures truly represent material moving sunward, they are hard to explain using only dust. Solar radiation pressure always pushes dust particles away from the sun. For dust to move inward, it would have to be subject to some other force overwhelming radiation pressure. Gas behaves differently. Gas molecules are not pushed by radiation pressure in the same way that dust grains are. If the night side of the nucleus, the side facing away from the sun, is outgassing strongly, the gas it releases could be directed toward the sun. In that case, jets from the night side would travel sunward, even though dust associated with them would still tend to be blown outward. That line of reasoning leads to another question. Why would the night side be outgassing strongly in the first place, with no direct solar illumination? One suggestion is that heat conducted through the interior of the nucleus can warm subsurface reservoirs of volatile material, allowing them to sublimate and vent even when the surface above them is cold and dark. Another suggestion is that the interior of 3I Atlas may be warmer than its surface for some reason, perhaps due to trapped heat or exothermic chemical processes. A more speculative idea is that there could be some kind of internal heat source. At this point, we are at the edge of what standard comet physics can easily explain. The observed jet geometry, the continuity of the features, the presence of apparent antitails, and the lack of clear rotational signatures together form a pattern that does not fall neatly into any single natural model. It may be that several mechanisms are operating at once, creating a complex pattern that no simple theory can capture. There is one more possibility, one that many researchers are cautious about raising in public but that cannot be completely ignored. What if some of the jets are not natural outgassing at all? Technological thrusters, such as those used on spacecraft, produce tightly collimated jets. They maintain direction regardless of rotation because their orientation can be controlled actively rather than being set by which parts of a surface happen to be in sunlight. Such thrusters can point in any direction, toward the sun or away from it as needed. To be clear, this is not a claim that 3I Atlas is an artificial object or that this explanation is correct. It is simply a recognition that the thruster analogy fits some aspects of the observations at least as well as the more conventional natural explanations that have been proposed so far. Right now, the safest thing we can say is that the jets from 3I Atlas are behaving in ways comet jets are not expected to behave. They hold their narrow shapes over distances where a normal outflow should spread and soften. Some of them point into regions that, under simple sunlight heating, should not be strongly illuminated. They show no clear sign of the regular on and off pattern that a steadily rotating nucleus should stamp onto the gas. Instead, they carve smooth, continuous lines through space. The next observations will be important for understanding what is really happening. High-resolution images from the Hubble Space Telescope and the James Webb Space Telescope during the December close approach may reveal the fine structure inside these jets. Spectroscopic measurements, which split the light into its colors, can show how fast the gas and dust are moving. If the material drifts outward at a few hundred meters per second, roughly what we expect from thermal outgassing of ices, that would support a natural interpretation. If instead the material races away much faster, closer to what we see from rocket exhaust, the implications would be very different. For now, we have images that show something nobody predicted: 7 distinct jets emerging from an interstellar visitor, forming patterns that do not fit comfortably inside our current picture of comet behavior. Whatever 3I Atlas is, its activity does not match the simple idea of a dirty snowball quietly boiling in sunlight, and the strange patterns do not end with the jets. On November 20th, another set of images revealed something even harder to explain. In these frames, observers found linear features forming a clear X shape, extending roughly perpendicular to the line between the sun and the object. The lines trace paths that may represent material peeling away from the main body, something that might still be traveling alongside 3I Atlas as it moves outward toward Jupiter. In the early hours of November 20th, 2025, around 4:15 Coordinated Universal Time, the same European team that had captured the 7-jet structure days earlier pointed their instruments at 3I Atlas again. Michael Yeager, Gerald Raymond, and Enrico Prosperi combined about 20 long exposures, each lasting around 100 seconds, to build up enough signal to detect faint structures far from the nucleus. When they processed the data, they found an image that quickly spread through observatories and research groups around the world. In that image, 4 clear linear features extend outward from the central bright region. 2 line up roughly along the sunward and anti-sunward directions, forming what looks like a tail and an anti-tail. The other 2 run sideways, close to right angles to the sun line. Together, the 4 lines form a pattern that strongly resembles the letter X wrapped around an interstellar object. The simplest explanation, and the one many researchers favored first, is that the sideways features are not part of 3I Atlas at all. Earth orbit is crowded with artificial satellites. When a satellite crosses a telescope's field of view during a long exposure, it leaves a straight streak. If more than one satellite passes through during a sequence of images, their trails can intersect. Under this view, the X is just a chance alignment of satellite streaks laid over the comet. There is some support for this idea. Near the bottom of the November 20th image, a 3rd linear feature appears that does not clearly connect to the central glow. It looks like the kind of streak created by a satellite passing through the frame. That makes it reasonable to ask whether all the lines might have the same cause. However, there are problems with explaining the whole X as satellite contamination. The 2 main sideways lines are oriented symmetrically around the nucleus. They appear to pass through the central brightness and extend similar distances on opposite sides, as though they originate from 3I Atlas rather than simply crossing the field at random. The odds that 2 unrelated satellites would cross the exact center of the target from nearly opposite directions during the same observing run are low. A stronger challenge comes from earlier data, when NASA released high-resolution images from the High-Resolution Imaging Science Experiment camera on the Mars Reconnaissance Orbiter, taken on October 2nd, while 3I Atlas was near Mars. Those data showed a similar pattern. The high-rise images revealed the nucleus, surrounded by a glow that extended in multiple directions, including features that resemble sideways arms of an X. Because these images were taken from Mars orbit, no Earth-orbiting satellites could have produced those lines. Whatever caused the X-like structure in the October data must be connected to 3I Atlas or to its immediate environment. So the question returns: what are we actually seeing? One natural hypothesis is that the linear features trace the paths of fragments that have detached from the main nucleus. Comets do break apart. Some split into multiple pieces when they pass close to the sun. Tidal forces, thermal stresses, and sudden releases of trapped gas can all fracture a nucleus. Volatile pockets buried below the surface can explode, launching chunks of material outward. If fragments separated from 3I Atlas near perihelion around October 29th, they would have had roughly 3 weeks to move outward by the time of the November 20th observation. At separation speeds of a few hundred to about 500 meters per second, a fragment can travel on the order of 1,000,000 kilometers over that interval. That distance matches the approximate length of the linear features. The geometry also fits, fragments moving away from the main body in opposite directions, with slightly different velocities, would leave behind streaks that extend perpendicular to the primary tail. Each fragment, acting like a small comet, would trail its own faint coma and dust tail. When you trace those lines back, they intersect near the parent body, forming an X centered on the nucleus. Fragmentation, however, carries its own implications. If the nucleus is shedding sizable chunks, we might expect to see direct signs of that breakup in other images. Yet, the post-perihelion observations do not clearly show multiple bright cores. On November 11th, comet specialists David Jewett and Jane Liu obtained images of 3I Atlas. Their data show what looks like a single dominant source of light, not several separate nuclei. There is no obvious swarm of large fragments, no bright debris field. At the resolutions available, the object appears as one coherent body continuing on its path. This creates a tension in the interpretation. The X-shaped pattern hints at material departing from 3I Atlas in more than one direction, while the direct imaging suggests that the main nucleus remains intact. One way to reconcile these facts is to assume that any fragments are too small to stand out as separate points of light. If they are only a few hundred meters across or smaller, they would be faint compared with the main nucleus and would blur into the surrounding coma. In that case, we would see only the trails they leave, not the fragments themselves. Another option is that the X is not made by physical fragments at all, but by a complex pattern of outgassing from different parts of the surface. If 3I Atlas has several active regions, each producing a strongly collimated jet, the combination of these jets could create the appearance of straight lines in different directions. The intersecting pattern might then be an effect of jet geometry and viewing angle rather than direct evidence that pieces have broken away. A third, more controversial possibility is that the linear features are the tracks of objects that were intentionally released from 3I Atlas. In this scenario, small probes or devices might have been deployed near perihelion to take advantage of the high speed and changing gravitational environment. These objects would travel on paths very close to that of the parent body, slowly separating as their slightly different trajectories carry them farther apart. Over weeks, their paths would draw lines through space, similar to those seen in the images. This idea is speculation, not a claim. There is no direct evidence that 3I Atlas is artificial. No repeating radio signals, no narrowband transmissions, no clear signs of manufactured materials have been detected so far. At the same time, there is also no definitive proof that every feature we see must be natural. The unusual patterns are compatible with both natural and artificial explanations, and careful science requires that we leave that uncertainty on the table. If many small objects were being released from 3I Atlas, we would expect them to be small enough to escape detection as individual point sources, to travel at speeds close to that of the main body so they stay near it for weeks or months, and to leave trails that line up with the geometry of the orbit rather than pointing in random directions. The existing X pattern is at least consistent with these conditions. The features are faint. Their lengths match what slow separation speeds would produce over a few weeks, and their orientations, roughly perpendicular to the sunline, would naturally carry objects away from the parent path while still keeping them in related orbits. This is not firm proof of anything. It is circumstantial evidence that keeps several possibilities open. The global monitoring campaign now in progress will help clarify the situation. As part of the International Asteroid Warning Network effort, observatories across several continents are collecting images and tracking changes in the coma and jet structures of 3I Atlas through January 2026. If the X-shaped features persist and evolve in ways that match physical objects moving along calculated paths, that would support the idea of fragments or other discrete bodies. If instead the features fade, shift unpredictably, or fail to show up in independent datasets, the case for instrumental artifacts or satellite streaks becomes stronger. The December 19th close approach to Earth will be especially valuable. At a distance of a little under about 270 million kilometers, 3I Atlas will be closer than at any time since its encounter near Mars. Large telescopes on Earth and in space will have their best chance to resolve fine details in the coma and to search for any small companions. If there are many objects traveling alongside the main nucleus, this will be the prime window in which to detect them directly or to see their influence on the surrounding material. Looking further ahead, there is also the question of what will happen when the object reaches Jupiter's space. If fragments or probes separated from 3I Atlas near perihelion, their paths will have diverged slightly from that of the parent body. Over the months between the late October solar passage and the March 2026 encounter with Jupiter, these small differences will build up. By the time the whole group enters Jupiter's neighborhood, the objects may be spread over millions of kilometers. This is where the earlier discussion of the Hill radius becomes relevant again. If the main body of 3I Atlas passes just outside Jupiter's gravitational capture zone, some of the smaller objects with slightly different trajectories might cross just inside it. Those that do so with the right combination of position and speed could be captured. They might end up as new long-term residents of the Jovian system, while the parent body continues onward and eventually leaves the solar system. The scenario is speculative, but it is also physically plausible. It does not require any new physics or violations of known laws. It only requires that 3I Atlas be more than a passive chunk of interstellar ice and rock. In that sense, the debate about the X-shaped features, the jets, and the Hill radius is really a debate about a larger question: whether this object is simply another rare natural visitor, or whether it could be something with a purpose we do not yet understand. The fragmentation debate will continue until more data arrive. At the moment, the evidence points in different directions at once. We see X-shaped features that could be simple satellite streaks, yet they also line up in ways that suggest trails from material moving out from the nucleus. In some images, 3I Atlas looks like a single intact body. In others, it is wrapped in structures that look like departing streams. All of this plays out on a path that carries the object toward Jupiter's space in March of 2026. To know which picture is closer to reality, we need time, steady observations, and the discipline to let the measurements, not our expectations, lead the way. If many small objects are peeling away from 3I Atlas, that process is not a future event. It would be happening now. Each day that passes, those possible fragments drift farther from the parent body. Their orbits slowly diverge. By the time of the close approach on December 19th, the separations could be large enough for large telescopes to resolve. If we do see a swarm of companions, the whole story of this visitor will change. But to interpret such a finding, we have to understand what the physics demands. That is why astronomers talk about the mass budget of 3I Atlas, the comparison between how much material should have been lost and how much we can actually detect. This is where the missing mass paradox appears. The paradox is simple to state. When gas escapes from a comet, the comet must recoil. Momentum is conserved, so the push on the gas and the push on the nucleus are equal and opposite. This is Newton's third law, confirmed in experiments and spacecraft navigation again and again. If we measure an extra acceleration on a comet, we can work backward to ask how much gas must have been expelled to create it. In the case of 3I Atlas, the Jet Propulsion Laboratory has measured a small but definite non-gravitational acceleration near perihelion. In plain language, the object felt a gentle, steady shove, amounting to only a few hundredths of a millimeter per second of speed change each second. That sounds tiny, but over many days, such a shove can noticeably bend the orbit. To get that effect through natural outgassing, the nucleus must throw off mass at a certain rate. The logic is straightforward. For a given total mass, the slower the gas leaves, the more mass must be lost to reach a given acceleration. The faster the outflow, the less mass is needed. If we know the acceleration, the typical gas speed, and the mass of the nucleus, we can estimate the total mass loss. The gas speed is the easiest part. For ices heated to the temperatures that 3I Atlas experienced near the Sun, thermal models and comet observations suggest outflow speeds of a few hundred meters per second. A commonly used value is about 400 meters per second at around 200 Kelvin. The total mass of the nucleus is harder, but there are strong clues. Before perihelion, from May through September, 3I Atlas was already outgassing. The James Webb Space Telescope measured a mass loss rate of roughly 150 kilograms per second in early August. That rate should have produced some non-gravitational acceleration, yet careful fits to the orbit in that period show none that stands above the noise. The simplest way to make those facts agree is to assume that the nucleus is very massive. If it is heavy enough, then losing 150 kilograms per second hardly changes its motion, and the resulting acceleration falls below our detection limit. Using this idea, Avi Loeb and collaborators derived a lower limit on the mass of 3I Atlas. Their estimate is that it must have at least about 33 billion tons of material. That is tens of billions of tons, a huge amount for an object only a few hundred meters to a few kilometers across. Such a mass implies an unusually high density. Most comets in our solar system are light and porous, mixtures of ice and dust, with many voids, more like loosely packed snow than solid rock. The inferred density of 3I Atlas, if that mass estimate is right, is higher than the density of rock. That already sets it apart from the standard comet picture. But the real difficulty comes when we put this mass together with the measured non-gravitational acceleration around perihelion. A massive object is harder to accelerate. If 3I Atlas truly weighs at least 33 billion tons, then to give it the observed extra shove near perihelion, outgassing must have carried away a very large amount of momentum. When we turn that requirement into a mass loss estimate, the result is that the nucleus should have lost at least 10 to 15% of its total mass during the close solar passage. 10% of 33 billion tons is about 3.3 billion tons. 15% is around 5 billion tons. So the simple momentum calculation says that billions of tons of material should have been ejected in the form of gas and dust. That material would spread out into a huge coma and tail. It would scatter sunlight and glow as an enormous envelope around the nucleus after perihelion. What we actually see is much less. Post-perihelion images do show a coma, multiple jets, and tail and anti-tail features stretching over millions of kilometers. But when astronomers convert that brightness into a mass estimate, they find only a small fraction of what the momentum argument demands. The best current estimates suggest that the total mass in visible dust and gas is at most in the tens of millions of tons. That is well under 1% of the 5 billion tons that should have been expelled if the standard outgassing model is correct. In other words, more than 99% of the expected ejecta is missing. This gap between what should be there and what we see is the missing mass paradox. Either our understanding of the object's mass, its gas speeds, or the source of the acceleration is incomplete, or there is far more material present than our current observations reveal. One way out is to argue that the nucleus is not as heavy as the pre-perihelion data suggest. If the true mass is much lower than 33 billion tons, then the amount of mass needed to explain the perihelion acceleration would also be much lower. That would ease the crisis. This idea usually comes with the suggestion that early outgassing was arranged in such a way that there was very little net push, so the lack of detected acceleration before perihelion does not really require a high mass. The trouble is that the pre-perihelion orbit is tightly constrained. It is based on thousands of measurements from many observatories to hide a significant non-gravitational acceleration in that data with a light nucleus. The outgassing would have to be almost perfectly symmetric. Jets would need to fire in opposite directions with nearly equal power, canceling each other to a high degree. For a natural, irregular body, such fine balance looks unlikely, though not impossible. Another option is to raise the gas speed. If gas leaves at, say, 600 or 800 meters per second instead of 400, each kilogram of gas carries more momentum, so fewer kilograms are needed. Carbon monoxide ice can naturally produce higher outflow speeds because it sublimates at lower temperatures. Spectra of 3I Atlas hint that carbon monoxide may be present along with carbon dioxide and water. A faster outflow would reduce the needed mass loss, but only by a factor of order 2. We still end up needing on the order of billions of tons of material, far above the tens of millions of tons that we can account for in the visible coma and tails. A more radical possibility is that the acceleration is not driven by simple sublimation at all. If some kind of technological propulsion were at work, the exhaust speed could be much higher than that of thermally driven gas. Chemical rockets can have exhaust speeds of several kilometers per second. Electric or ion thrusters can reach tens of kilometers per second. At those speeds, the same change in momentum can be achieved with much less expelled mass. A rocket exhaust at 3 kilometers per second would need only a few percent as much propellant as sublimating ice at a few hundred meters per second. An ion engine at 30 kilometers per second would need roughly 1% as much. In that case, the small amount of visible material around 3I Atlas could be enough to account for the measured acceleration, and the missing mass paradox would vanish. To say this plainly, this is only a logical possibility, not a claim about what the object really is. The data do not show clear signs of engines. There is no repeating radio beacon, no obvious artificial signal. But the math does tell us that if the exhaust speed were much higher, the mass budget problem would be easier to solve. Scientists are trained to be cautious with such hypotheses. The usual approach is to prefer natural explanations and to invoke more complex scenarios only when simple ones fail clearly. At the same time, ignoring a mismatch between theory and observation is not good science either. Any final explanation for 3I Atlas will have to explain why so much mass seems to be missing. One more natural way to soften the paradox is to suggest that the missing material is there but hard to see. Comet outgassing produces both gas and dust. Gas is faint in reflected light and often only shows up in narrow emission lines at specific wavelengths. Dust, on the other hand, scatters sunlight well and dominates the visible appearance of a comet. If 3I Atlas expelled a cloud that is mostly gas with very little dust, the total mass around the nucleus could be much larger than the brightness of the coma suggests. Radio telescopes have indeed detected hydroxyl molecules near 3I Atlas, a sign that gas from water is present. But turning those radio detections into a precise total gas mass is difficult. The uncertainties are large. In principle, a massive low-density gas cloud could be hiding in plain sight. However, modern space telescopes complicate this idea. Instruments like the James Webb Space Telescope and the planned SPHEREX mission are designed to pick up specific infrared wavelengths where common comet gases, such as carbon dioxide and water, emit strongly. Carbon dioxide has a strong feature near 4.3 micrometers. Water shows features near 2.7 micrometers. If billions of tons of gas were present, rich in these molecules, those features should stand out clearly in the spectra. So far, the spectroscopic data do not show the kind of strong broad signatures that such a huge hidden cloud would create. For now, the missing mass paradox remains unresolved, and it stands as one of the deepest open questions in the story of 3I Atlas. We are left with a problem that does not yet have a clean answer. The non-gravitational acceleration of 3I Atlas is real. The way we use momentum to turn that acceleration into a mass loss estimate is straightforward. The gap between the expected mass of ejected material and the much smaller amount we actually see is also real. Put together, these pieces tell us that something in our current picture is incomplete. In the coming weeks, new observations will sharpen the numbers. The Hubble Space Telescope and the James Webb Space Telescope are scheduled to watch 3I Atlas near its closest approach to Earth on December 19th. Spectrometers will measure how fast different gases are flowing away. Imaging systems will follow how the coma and the jets change over time. It is possible that these data will reveal a large hidden gas cloud or some other natural answer to the missing mass problem. It is also possible that the discrepancy will remain, forcing us to consider explanations that lie outside the comfortable range of our usual models. If that happens, it may be because 3I Atlas is telling us something about itself that we do not yet know how to interpret. The universe is vast, and our direct experience of interstellar objects is tiny. In all of recorded astronomy, we have seen only 3 confirmed bodies that came from interstellar space. That is not a big sample. If even one of those 3 turns out to be deeply unusual, perhaps we should not be surprised. For many researchers, the missing mass paradox acts less like a closed door and more like an invitation. It invites us to look more closely at the data, to test our assumptions, and to keep an open mind about possibilities that might otherwise be dismissed too quickly. The measurements are telling us that something does not fit neatly. Our job is to find out what. While astronomers were wrestling with the mass budget, another set of instruments was listening instead of looking. They were listening at radio frequencies that have a special history in the search for extraterrestrial intelligence. Frequencies where water-related molecules naturally emit and absorb radiation. These sit in a part of the spectrum known as the water hole, the same region where, in the late 1970s, a radio telescope in Ohio picked up a signal so unusual that the astronomer who first saw it wrote a single word in the margin of the printout. Wow! In the early hours of October 24th, 2025, 64 dish antennas in the Karoo region of South Africa were pointed at a patch of sky only about 3.76 degrees from the sun. The Meerkat radio telescope, one of the most sensitive arrays now operating on Earth, was trying to do something that had never been done before: detect radio waves from an interstellar object. 3I Atlas was 5 days away from perihelion, racing toward its closest approach to the sun, heating up and releasing gas. As it transformed from a cold wanderer into an active body shedding material into space. Meerkat was listening. What it heard was both exciting and, for anyone hoping for an obvious artificial signal, sobering. At radio frequencies around 1665 MHz and 1667 MHz, the telescope detected narrow absorption features, small dips in the radio spectrum at very specific frequencies. These dips occur exactly where hydroxyl radicals, molecules made of one oxygen atom and one hydrogen atom, are known to absorb background radio noise. The amount by which the lines were shifted in frequency by the Doppler effect, about 15.15 kilometers per second, matched the expected motion of 3-1 Atlas relative to Earth on that date. This made Meerkat's observation the first confirmed radio detection of an interstellar object. Before letting our imaginations run ahead, we should be clear about what this means. Hydroxyl forms when water vapor is broken apart by ultraviolet light from the sun. When water ice on or near the surface of a comet sublimates, the vapor flows out into space, and some of those water molecules are split into hydrogen and hydroxyl. Any comet that passes close enough to the sun to warm its water ice will produce hydroxyl radicals. The Meerkat detection tells us that 3I Atlas is venting material that leads to hydroxyl when exposed to sunlight. In that sense, this is exactly what we would expect from a comet that contains water. It confirms that, whatever else may be unusual about this object, at least one part of its behavior is ordinary. It is outgassing, and some of that gas comes from water or related compounds. The frequencies involved are what make the story more interesting. The hydroxyl lines at 1665 and 1667 MHz lie in a relatively quiet band of the radio spectrum. On one side is the well-known hydrogen line at about 1420 MHz. On the other side are other hydroxyl features near 1720 MHz. Between these lines is a band where natural radio noise is relatively low. Astronomers call this band the water hole. Hydrogen is the most common element in the universe. Hydroxyl, combined with hydrogen, makes water, which is essential for life as we know it. The radio frequencies framed by the hydrogen and hydroxyl lines therefore form a kind of natural marker. Any technologically advanced civilization with radio telescopes could notice that this band is quiet, easy to observe, and symbolically linked to water and life. For that reason, early studies of how to search for extraterrestrial intelligence suggested that if any civilization wanted to send a signal that others might recognize, the waterhole would be an obvious place to transmit. This idea was laid out clearly in the early 1970s in a report known as the Cyclops Study, a NASA-funded analysis of large radio arrays. The waterhole concept shaped much of the early search for extraterrestrial intelligence work. It is one reason the Big Ear telescope in Ohio was tuned to frequencies near 1420 MHz on August 15, 1977, when it recorded the signal that later became known as the WOW signal. That history is why many scientists and members of the public pay close attention when anything interesting happens at waterhole frequencies. In the case of 3I Atlas, there is an extra coincidence. The region of sky from which this object arrived is within about 9 degrees of the direction in the constellation Sagittarius, where the WOW signal came from. Both point toward the same general part of the Milky Way. Both involve activity in or near the waterhole band. And now 3I Atlas has produced a clear radio detection in that band just days before its closest approach to the Sun. It is easy, with all of these alignments in mind, to feel that coincidences are stacking up. At the same time, it is important to stay grounded. The Meerkat detection is hydroxyl absorption, not a narrowband beacon. It is entirely consistent with natural cometary outgassing. The shape of the lines, their widths, and their Doppler shifts match what we expect from gas moving with the bulk flow of a comet's coma. Nothing in the raw data requires a technological explanation. Avi Loeb, who helped motivate the Meerkat observations, has made a more cautious point. The hydroxyl features were detected only on October 24th. Earlier, Meerkat attempts on September 20th and September 28th did not show a clear signal. The hydroxyl absorption appeared only a few days before perihelion, at exactly the time when the comet's activity should have been ramping up as it heated in stronger sunlight. For a natural comet, this is expected behavior. As the nucleus warms, outgassing increases. More water vapor means more hydroxyl, and the hydroxyl lines grow strong enough to detect. Seen this way, October 24th marks a normal turning point in the life of an active comet approaching perihelion. Loeb's question is whether we know enough yet to say that the hydroxyl production is smooth and simple. With only a few radio observations, we cannot tell if there are brief bursts of extra activity or unusual changes in the way gas is being released. The solution he proposes is straightforward. Keep observing. If we want to rule out strange patterns, we need more than a handful of snapshots. On November 5th, Meerkat turned to 3I Atlas again, this time searching not for broad absorption features, but for narrowband signals of the type we associate with artificial transmitters. A special processing system designed for techno-signature searches combed through the data in real time. It flagged more than 23,000 candidate signals. Every one of them turned out to be terrestrial radio frequency interference. Human-made sources such as satellites, aircraft, and ground-based transmitters that happen to fall in the telescope's field of view. None could be traced to 3I Atlas. The sensitivity of this search was high. The effective power limit was on the order of 0.17 watts at the distance of 3I Atlas, roughly the same as the output of a mobile phone, but projected across about 334 million kilometers of space. If there had been a steady, narrowband radio beacon on the interstellar object at that power level or higher, operating within the observed frequencies during that observation, Meerkat should have seen it. It did not. That does not prove that no artificial transmitter is present. A device could have been switched off at the time. It could transmit only in short bursts, or at frequencies outside Meerkat's coverage, or using encoding methods that our software does not recognize as signals. Absence of evidence is not the same as evidence of absence. Still, the combination of results is informative. We have a clear hydroxyl absorption signal consistent with natural outgassing, and we have no sign of artificial radio emission above a fairly low threshold. The simplest way to fit these facts together is to say that 3I Atlas is behaving like a comet in the radio band. It outgasses material that includes water, which produces hydroxyl. It does not emit strong, steady artificial signals in the frequencies checked so far. Under this reading, 3I Atlas is an unusual interstellar comet, but still a comet. Even so, the waterhole connection and the WOW signal alignment linger in the background. They sit alongside the strange jets, the missing mass, and the trajectory coincidences as part of a broader pattern that some researchers find hard to ignore. Each piece on its own has a natural explanation. Together, they encourage more questions. To see why the WOW signal keeps returning in these discussions, it helps to recall what happened in 1977. On August 15th of that year, the Big Ear radio telescope recorded a 72-second burst of radio energy at a frequency of about 1,420.456 megahertz, very close to the hydrogen line. The signal was strong, more than 30 times the background noise. It appeared to come from the direction of the constellation Sagittarius. It did not repeat. Jerry Eman, the astronomer who first spotted the strange pattern on the printout, circled the key row of letters and numbers and wrote a single exclamation in the margin, "Wow." That handwritten note gave the event its name. For nearly 50 years, the WOW signal has remained unexplained. Follow-up observations with many telescopes have searched the same patch of sky at similar frequencies. None has found a convincing repeat. Natural explanations have been proposed, from comets releasing hydrogen to unusual stellar flares to complex propagation effects in interstellar space. None has fully solved the mystery, and so the WOW signal endures as one of radio astronomy's most famous unsolved puzzles. The possible connection between 3I Atlas and the WOW signal was raised early in the observing campaign by Avi Loeb and others. When astronomers trace the incoming path of this interstellar object backward across the sky, it points to a region separated by only about 9 degrees from the location associated with the WOW signal. On the full dome of the sky, 9 degrees is a fairly small separation. It is close enough to invite the question, could these two mysteries be related in some way? One tempting idea is that the WOW signal might have been a transmission from whatever civilization, if any, sent or steered 3I Atlas. In that picture, the signal detected in 1977 could be seen as a kind of calling card, and the arrival of the object in 2025 as a follow-up visit almost 5 decades later. It is an image that appeals to the imagination. But when we check the numbers, the timing does not work. During its approach, 3I Atlas moved at roughly 200 kilometers per second relative to the Sun. At that speed, even crossing the distance between nearby stars would take tens of thousands to millions of years, depending on how far away the source is. No object traveling at 200 kilometers per second could have left the WOW signal region in the late 1970s and reached our solar system in only 48 years. A direct link in which 3I Atlas itself sent the WOW signal is ruled out by basic travel times. The object simply could not have been anywhere near us in 1977. A softer, indirect connection is harder to dismiss. It is possible that 3I Atlas and the WOW signal both originate from the same broad region of the Milky Way. If some distant civilization or other long-lived phenomenon exists in the direction of Sagittarius, then a radio signal and an interstellar object coming from roughly that area might be different expressions of the same underlying source. In that case, the 9-degree angular separation would not represent a cause and effect relationship, but 2 hints pointing toward the same patch of sky. At this stage, such ideas are speculation. They rely more on pattern seeking than on hard data. We do not know the true distance or origin point of the WOW signal. We do not know the full outbound trajectory of 3I Atlas, beyond the fact that it arrived from the general direction of Sagittarius. The 9-degree separation may turn out to be meaningful, or it may mean nothing more than the fact that many interesting things can come from the same quadrant of the sky. For now, the only honest statement is that the approach angle of 3I Atlas and the WOW signal direction form an unusual curiosity, not a proven connection. What we can say with more confidence is that radio observations of 3I Atlas have added another layer to an already complex story. We know that the object is active at radio wavelengths. It produces hydroxyl absorption in the waterhole frequency band, exactly where water-related molecules are expected to leave their fingerprints. We also know that no narrowband artificial transmissions have been detected from it at the sensitivity limits of current telescopes. Its incoming path happens to lie near the WOW signal direction, and that coincidence remains on the list of open questions rather than a solved mystery. The monitoring effort continues on several fronts. In March of 2026, 3I Atlas will pass near Jupiter. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, will be about 53 million kilometers from the interstellar visitor at that time. Juno carries sensitive radio and plasma instruments that can detect changes in the environment around Jupiter, and in principle, it could pick up radio emissions from 3I Atlas if they fall within its operating bands. Juno has access to frequency ranges and vantage points that Earth-based arrays such as Meerkat cannot easily match. If there are radio signals to be found at those frequencies, Juno may be in a position to detect them. Until then, astronomers will continue to watch and listen from Earth and from near-Earth orbit. Each new dataset adds context. As with much of science, the guiding attitude is simple: collect evidence, compare models with reality, and remain open to the possibility that nature might still surprise us. While the radio story unfolded, the optical and ultraviolet images were telling a parallel story, one complicated by events on the ground. Some of the most important pictures of 3I Atlas taken so far sat unreleased for more than 40 days because of a government shutdown in the United States. During that time, researchers knew that a spacecraft at Mars had captured valuable data, but official channels could not share the results. The key instrument in question was the high-resolution imaging science experiment, often called HiRISE, aboard NASA's Mars Reconnaissance Orbiter. On October 2nd and October 3rd of 2025, as 3I Atlas passed within roughly 29 million kilometers of Mars, HiRISE was pointed toward the interstellar visitor. This was the closest that any spacecraft would come to 3I Atlas during its entire passage through the solar system. From that range, the camera's spatial resolution was on the order of 30 kilometers per pixel, a factor of about 3 better than what the Hubble Space Telescope could achieve from Earth orbit. Those images had the potential to reveal structure in the coma that no other instrument could see. But on October 1st, a government funding lapse triggered a shutdown that froze most of NASA's public-facing operations. Many websites stopped updating. Press releases were put on hold. The HiRISE data, though safely stored, remained inaccessible to the broader scientific community and to the public. As the days turned into weeks, frustration grew. Members of Congress, including Representative Ana Paulina Luna, wrote to NASA's acting leadership urging the release of the Mars images. Outside NASA, researchers such as Avi Loeb spoke out about the scientific cost of the delay. 3I Atlas is a once-in-a-lifetime visitor. Losing more than a month of analysis time during its brief stay near Mars and Earth felt, to many, like an avoidable setback. After 43 days, on November 19th, NASA held a press briefing and finally released the HiRISE images. The results were both useful and, in some ways, disappointing. In the main frame, 3I Atlas appears as a small fuzzy patch against the dark background. Because the spacecraft experienced slight motion, or jitter, during the observing sequence, the target is smeared across several pixels. The bright inner region of the coma is visible, but the nucleus itself is not resolved as a sharp point. There are no crisp edges, no clearly separated fragments, only a compact glow. Even so, the images carry important information. The coma of 3I Atlas fills the entire HiRISE field of view. Only the central region shows up clearly at the chosen exposure time, but the overall brightness profile indicates that the cloud of material extends much farther than the frame can capture. This confirms that during the Mars flyby, the interstellar object was already surrounded by a large, active envelope of gas and dust. The shape of the coma is also revealing. It is not perfectly round. There are hints of extension in more than one direction, suggesting that focused jets were already shaping the outflow. The X-shaped patterns that ground-based observers would later see more clearly in November may have been developing even then, faintly present in the Mars-era data. The full picture from Mars includes more than just HiRISE. NASA's MAVEN spacecraft, which studies the Martian atmosphere, also took advantage of the opportunity. On September 28th, its imaging ultraviolet spectrograph observed 3I Atlas. In ultraviolet light, hydrogen atoms show up strongly, and MAVEN detected a cloud of hydrogen surrounding the object. This is exactly what we expect when water ice sublimates and the resulting water vapor is broken apart by sunlight. In the MAVEN images, 3I Atlas appears as a dim source on one side, Mars as a bright streak on the other, and a band of interplanetary hydrogen stretching between them. Together, these features show that water-related activity around 3I Atlas was real well before perihelion. On the Martian surface, the Perseverance rover added a small but historic observation. On October 4th, its Mastcam-Z instrument took a very long exposure of the sky above Jezero crater. Because the camera does not track moving targets, stars appear as elongated streaks as Mars rotates during the exposure. Against this pattern, 3I Atlas shows up as a faint, slightly blurred point. The image contains little scientific detail beyond confirming the object's position and brightness, but it is notable as the first time a rover on another planet has photographed an interstellar object. During the period when NASA's own high-resolution data was still under wraps, another space agency stepped in. China's Tianwen-1 mission, which also orbits Mars, used its high-resolution camera to image 3I Atlas on October 3rd from about the same distance of roughly 29 million kilometers. Those images, released promptly, showed a central condensation surrounded by a coma a few thousand kilometers across. An animation built from a series of half-minute exposures captured the motion of the object against the background stars. Although the Chinese data had lower resolution than HiRISE, they demonstrated what could be done when images were shared quickly. Many scientists and commentators could not help comparing the two approaches. When NASA finally published its full Mars dataset in November, agency scientists emphasized that everything seen so far was consistent with a comet. At the press event, planetary scientist Tom Stadler addressed circulating rumors directly. The object, he explained, looks and behaves like a comet. It develops a coma. Its spectrum shows signs of volatile ices turning into gas, and its radio signature includes hydroxyl produced by water. In that sense, all of the available evidence points toward a natural cometary body. There is truth in that summary, but it is not the whole story. The images from Mars and from later ground-based campaigns do not show the nucleus directly. They show light scattered by the surrounding material. The estimated size of the solid body remains uncertain and is still based on upper limits rather than a clear measurement. The unusual geometry and continuity of the jets are not yet fully explained. The mass budget appears unbalanced. These are not contradictions of the comet hypothesis, but they are reminders that comet may be a broad category rather than a simple label. One more result from Mars quietly changed how well we know the path of 3I Atlas. The European Space Agency's ExoMars Trace Gas Orbiter observed the object several times between October 1st and October 7th. Unlike many Earth-based telescopes that see the object from roughly the same direction, the orbiter viewed it from a completely different vantage point in Mars orbit. By combining positions measured from two planets at once, navigators could triangulate the orbit much more precisely. The effect on the trajectory solution was dramatic. The uncertainty in the predicted position of 3I Atlas shrank by about an order of magnitude, from several hundred kilometers down to only a few tens of kilometers. That improvement feeds directly into calculations of how close the object will come to Jupiter, whether it passes just inside or just outside the Hill radius. and where exactly to point telescopes during the December 19th close approach. Taken together, the Mars observations draw a coherent picture of an object that, in many ways, is doing what a comet should do. As it approaches the Sun, it outgasses water and carbon dioxide. It builds a large coma and develops jets as volatile materials escape the surface. Its trajectory responds both to gravity and to the small extra push of escaping gas. If we looked only at these facts, we would describe 3I Atlas as an unusual comet from interstellar space. Unusual in its size, its speed, its composition, and its fine details, but still a natural fragment of another planetary system thrown out long ago and now passing through our corner of the galaxy by chance. We cannot end the story with Mars, because those observations happened before perihelion, before the strong non-gravitational acceleration was measured, before the missing mass paradox appeared, before the 7 jets and the X-shaped structures showed up in later images. The Mars data show 3I Atlas in a relatively quiet state. What followed was not quiet at all. By the time the delayed high-resolution images were finally released, the object seen from Earth had already changed, becoming more active, more structured, and more anomalous than the version that passed Mars. Now the scientific community is preparing for the next major observing window. On December 19th, 3I Atlas will pass within about 269 million kilometers of Earth, closer than it has been since it left the vicinity of Mars. The Hubble Space Telescope and the James Webb Space Telescope will both observe it. Ground-based observatories will track its motion. The International Asteroid Warning Network campaign will coordinate data from many instruments. This will be our best chance to probe what 3I Atlas really is, to test the trajectory models, to confront the missing mass problem, and to map the jet structures in detail. The measurements collected in December will shape how we understand this interstellar visitor for years to come. After that window closes, 3I Atlas will begin its long outward leg, heading toward its encounter with Jupiter in March, and then onward into the darkness between the stars, never to return. We have only a short time left in which to study this object closely. Once it is gone, we will be left with whatever records we manage to gather now. The Mars images were a preview. The December observations will be the most detailed chapter that Earth-based and near-Earth instruments can write. What happens when 3I Atlas reaches Jupiter space? And what happens after it leaves the planetary region entirely? Will be seen, if at all, from much greater distances. Yet the importance that agencies attach to this object is already clear. The United Nations considers it significant enough to build an exercise around it. For the first time, the international planetary defense community has organized a formal drill centered on an interstellar body. On November 27, 2025, the International Asteroid Warning Network, a United Nations-endorsed partnership of space agencies and observatories, activated a focused observing campaign for 3I Atlas. This is the 8th such coordinated exercise since the network was established in 2017, but it is the first time the target is an interstellar object. The network exists to coordinate global responses to potential asteroid and comet hazards and to support the planning that would be vital if a real threat ever appeared. To stay ready, it runs regular exercises. In most years, it chooses a near-Earth asteroid as a practice case. Observatories measure its position, share data in common formats, and update trajectory models. Agencies rehearse how they would exchange information in an emergency. The goal is to check procedures and communication before a crisis, not during one. The 3I Atlas campaign is different in one obvious way. This object is not a threat to Earth. Its closest approach those roughly 269 million kilometers, keeps it safely distant. The impact probability is effectively zero. So why use it as an exercise target? The public documentation gives a clear answer. Comets and comet-like bodies with large comae and tails are harder to measure precisely than bare asteroids. Their extended structure can pull the measured center of light away from the true center of mass. For a comet on a path that might someday intersect Earth, small errors in position can grow into large errors in impact probability. The network wants to practice on a difficult case, and 3I Atlas certainly qualifies. Its hyperbolic orbit, with an eccentricity of about 6.14, is steeper and faster than the paths of ordinary solar system comets. Its active coma shows multiple jets and complex shapes that complicate the job of pinning down its exact position. Its interstellar origin means there are no old images to help refine the orbit. In almost every respect, it is an ideal stress test for the planetary defense system. The formal campaign runs from late November 2025 through late January 2026. Observatories on several continents have signed up to contribute, sending measurements in standardized formats so they can be combined easily. Although framed as an exercise, the work is very real. The effort will create the most detailed dataset we have on 3I Atlas, tracking the object for about 2 months as it moves away from the Sun. Those data will feed into improved trajectory models, better maps of how and where the object is outgassing, and sharper estimates of its physical properties. If there are oddities in the motion, this campaign is designed to find them. If the path begins to drift away from predictions, the combined measurements will reveal the change. If 3I Atlas behaves in a way no one has anticipated, this is the observing window in which that behavior is most likely to be documented. It is easy to see how some headlines have overstated what this means, suggesting that planetary defenses have been activated against 3I Atlas. The reality is simpler. Planning for a 2025 comet campaign began back in 2024 when 3I Atlas was discovered and its path became clear. It offered a rare opportunity. Choosing it as the focus of the exercise was an opportunistic decision, not a last-minute reaction. There is no hidden threat assessment, no quiet evacuation plan. The exercise is exactly what it appears to be, a chance to rehearse procedures on a scientifically interesting but harmless object. At the same time, the effort reflects how seriously the international community now takes planetary defense. Missions such as the DART impact test have shown that we can alter the path of a small asteroid. New survey projects are being built to find far more near-Earth objects, including ones that are dark invisible light. These investments rest on a simple recognition: major impacts have happened in Earth's past and will happen again. The question is not if, but when. And when that day comes, we will need the ability to detect, track, and, if necessary, deflect a hazardous object. Exercises like the 3I Atlas campaign are part of that preparation. They test coordination, communication, and the capacity to focus resources on a single target when it matters. There is another lesson in this exercise as well. Interstellar objects pose a different kind of challenge from the asteroids and comets that belong to our own solar system. For many near-Earth asteroids, we can trace their orbits years or decades into the future. We can see them long before any possible encounter and plan accordingly. Interstellar visitors do not give us that luxury. They arrive on steep, fast paths, are discovered only months before perihelion, and then they are gone. 3I Atlas was first noticed on July 1st, 2025, when it was already inside Jupiter's orbit. Only about 4 months passed between discovery and perihelion. If a similar object were ever found on a direct collision course with Earth, the warning time could be measured in months. or perhaps only weeks. The current campaign is, in part, a rehearsal for that scenario. It asks how quickly we can characterize a fast-moving target, how accurately we can project its future path, and how well agencies on different continents can coordinate their response. For this particular object, we are fortunate. 3I Atlas will pass at a large and safe distance. That gives us the chance to practice without the pressure of imminent danger. The next interstellar visitor may not be so cooperative. It is worth remembering how small our sample still is. So far, astronomers have confirmed only 3 interstellar objects. All 3 have been unusual in their own ways. The first, often called Oumuamua, showed non-gravitational acceleration without a detectable coma or jets. The second, Borisov, looked more like a standard comet with familiar activity and composition. 3I Atlas is larger and faster than both, and in several respects stranger than either. Its behavior near the Sun, its jets, its missing mass puzzle, and its future passage near Jupiter together form a combination that stretches our current understanding and invites us to keep asking questions as long as it remains within reach of our instruments. 3 confirmed interstellar objects are not enough to draw a firm pattern. They show that such visitors exist, but they do not yet tell us how typical or unusual they are. If future interstellar bodies keep arriving with strange properties, though, we will eventually have to ask harder questions. Is our current survey system biased toward finding only certain kinds of objects? Are we overlooking the ordinary ones and catching only the rare and dramatic cases? Or is there something genuinely unusual about the material drifting between the stars? The current international observing campaign will not settle these questions by itself, but it will push us a little further. Each image, spectrum, and position measurement adds to our understanding. Each new data point tightens the models we use to describe how 3I Atlas moves and behaves. Over time, as these data are combined with what we learn from future interstellar visitors, a clearer picture of the larger population will begin to take shape. For now, the exercise is serving its direct purpose. Observatories across the world are coordinating. Data are flowing into shared archives. Teams are updating orbital solutions and comparing them. The international community is rehearsing the steps it would have to take if a genuinely hazardous object were ever found. In the middle of this practice run, 3I Atlas is continuing its outward flight past the orbit of Mars, toward the main asteroid belt, and onward toward Jupiter. Each day it travels a little farther from the Sun and a little closer to its planned March encounter with the largest planet in our system. The next major milestone on that journey is December 19th, the date of its closest approach to Earth. That day will mark the point when our telescopes have their best view of this visitor. It may be the day when several of the current questions are finally answered, or the day when new puzzles appear. At that time, 3I Atlas will be about 269 million kilometers from Earth, a little under 2 astronomical units, almost twice the distance between our planet and the Sun. That is still far, but for an object that came from another star system, it is remarkably close. The astronomical community is preparing accordingly. The Hubble Space Telescope has observing time reserved. This long-lived observatory, operating for more than 3.5 decades, will point its instruments at 3I Atlas during the close approach window. Hubble's sharp vision at optical wavelengths is still unmatched by telescopes on the ground. Its images should reveal fine structure in the coma and jets that atmospheric blurring would hide. The James Webb Space Telescope will also take part. Its infrared instruments are well suited to measuring the chemical makeup of the gas and dust around the nucleus. By examining the infrared spectrum, Webb can tell us which ices are sublimating, at what rates, and in what proportions. Observations in August already showed that the coma is rich in carbon dioxide compared with water. The December spectra will test how that balance has changed after perihelion and during the outward leg. Large ground-based observatories, including major facilities in Chile and Hawaii, have scheduled their own campaigns. Smaller professional telescopes and experienced amateur observers are planning to contribute as well. At a visual brightness of about magnitude 10, 3I Atlas can be seen with modest equipment under dark skies, though it is currently in the morning sky and rises only a few hours before dawn. Observers will need to use the short window between its rise and the brightening of the eastern horizon carefully. As the month progresses, the object will climb higher each pre-dawn morning, lengthening the usable observing time. Around closest approach, the geometry should be favorable. For many viewers, the interstellar comet will be well placed against the stars of Leo. Scientists have several clear goals for this December push. One is to map the jet structure in finer detail. Post-perihelion images have already shown a complicated mixture of jets, tails, and anti-tails that do not line up in the simple ways seen in familiar comets. High-resolution data from Hubble, Webb, and large ground-based instruments may reveal whether the jets are coming from a small number of active regions on the surface, from fragments trailing the main body, or from some more complex arrangement. A second goal is to measure the current outgassing rates as accurately as possible. The non-gravitational acceleration near perihelion implies that 3I Atlas must have lost a significant amount of mass over a short time. Now that it is heading away from the sun and cooling, those mass loss rates should be decreasing. If the activity falls off in the way standard thermal models predict for a natural comet, that will support the idea that the unusual behavior can be explained by composition and geometry alone. If the activity stays higher than expected, or varies in unusual ways, more exotic explanations may need to be explored. A third aim is to search for fragments or companion objects. The X-shaped patterns seen in earlier images suggest that pieces may have separated from the nucleus and are moving along slightly different paths. With the improved sensitivity and resolution available during closest approach, even small fragments may stand out as separate points of light or as subtle distortions in the coma. If such companions are found, they will offer a window into the internal structure and strength of the nucleus. If none are detected, the case for other explanations of the X-shaped features will grow stronger. A fourth objective is to refine the trajectory further in advance of the Jupiter encounter. Every precise position measurement helps reduce the uncertainty in where 3I Atlas will be in March. The question of whether the object passes just inside or just outside Jupiter's Hill radius depends on these refinements. Small differences in the measured path now will translate into tens of thousands of kilometers of difference near Jupiter. The date of closest approach also creates favorable observing conditions. December 19th falls close to the northern winter solstice. Long nights and short days give observers at mid and high northern latitudes extended dark time. The moon will be a thin, waning crescent, rising after midnight and adding little interference. For much of the night, the sky will be dark, and the region of Leo hosting 3I Atlas will be free of significant moonlight. Even with these advantages, there is a sense of urgency. 3I Atlas is moving on a hyperbolic path, leaving the solar system. Its speed relative to the sun is tens of kilometers per second. Every day after closest approach, it will be farther away, a little fainter, and a little smaller on the sky. By mid-January, it will already be more difficult to resolve structure in the coma. By early February, only the largest telescopes will be able to follow it. By the time it reaches Jupiter's distance in March, the possibility of resolving fine details from Earth will be nearly gone. This is why December is so important. Each clear night in the coming weeks is an opportunity that will not come again for this object. The data gathered now will form the core record that future researchers will revisit when they study 3I Atlas in retrospect. Beyond the technical goals, there is a broader context. 3I Atlas is an object from another star system. It has spent perhaps billions of years traveling through the interstellar medium, preserving the chemical fingerprints of the place where it formed. By studying its composition and structure, we gain information about the conditions in a distant protoplanetary disk. The high ratio of carbon dioxide to water, the presence of carbon monoxide and other volatiles, and the way the object responds to solar heating all carry clues about its origin. If 3I Atlas turns out to be nothing more than a very unusual but natural comet, that conclusion will still teach us a great deal. It will expand the range of known comet properties and help refine our models of how planetesimals form and are ejected from their home systems. If, on the other hand, some of the anomalies remain unexplained even after the best December data are analyzed, then the close approach will mark the moment when the mystery deepens rather than resolves. In either case, the process will be the same. Observers will use the instruments available to them. They will collect the highest quality data they can. They will test competing explanations and discard those that do not fit. They will accept that some questions may remain open for years. That steady, careful work is how science progresses, especially when it meets something rare and difficult, like an interstellar visitor passing briefly through our skies. December 19th is approaching, and with it, the closest view we will ever have of 3I Atlas. After that, the next major moment comes in March 2026, when the object moves through the outer solar system toward Jupiter's expansive gravitational territory. Whatever questions remain about its motion, its mass budget, or its deeper nature, will eventually meet their most important test in that region. To understand why, it helps to consider Jupiter itself. This planet, more than 2.5 times as massive as all the others combined, sits about 5 astronomical units from the Sun. Its gravity reaches far into the surrounding space, shaping the paths of comets and redirecting passing asteroids. For roughly 4.5 billion years, Jupiter has acted as a guardian of the inner solar system, blocking some objects and guiding others away. In mid-March 2026, Jupiter will receive a visitor from beyond the Sun's domain. 3I Atlas is expected to pass within roughly 54 million kilometers of the planet, which places it near the outer edge of Jupiter's hill sphere, the region where the planet's gravity dominates over the Sun's influence. Whether the object passes slightly inside or slightly outside this boundary depends on trajectory refinements still underway. Whatever the final numbers show, the encounter will reveal something essential about how the object behaves under Jupiter's gravitational pull. If current models are correct and the object remains outside the hill radius, it will simply continue along its hyperbolic path. Jupiter will bend its trajectory slightly, adding a small gravitational boost before the object travels outward toward the Kuiper belt and, eventually, back into interstellar space. By the end of 2026, 3I Atlas would be far beyond Jupiter's orbit, receding steadily into the dark. If something deviates from those predictions, the implications could be significant. A measurable change in course, unusual timing in the non-gravitational acceleration, or any separation of smaller bodies that shift into Jupiter's gravitational influence would prompt questions that planetary scientists are not yet fully equipped to answer. Natural comets grow quieter as they move away from the Sun, and by March the object should be cool enough that any volatile activity has dropped sharply. A substantial course change at that distance would require careful explanation. A more subtle possibility involves the release of smaller objects. Earlier images with X-shaped patterns hinted at materials separating from the parent body. If such fragments exist, and if their paths differ even slightly, some might drift into Jupiter's Hill sphere, while the main body passes outside it. Those small objects, if present, could become gravitationally bound to Jupiter or its moons. They would be too small to detect directly during the flyby, and they might remain hidden for years. But if something foreign eventually appears in the Jovian system, an object with an unusual orbit or composition, astronomers would notice. Although such scenarios are highly speculative, they are considered because the job of scientific analysis is not to assume the answer, but to examine the full range of physically plausible outcomes. We have no evidence that 3I Atlas has released probes or that it contains anything artificial. These ideas remain possibilities only in the theoretical sense, illustrations of how scientists explore the boundaries of what could occur. The likelier scenario is simpler. 3I Atlas will pass by Jupiter quietly, altering its course only as gravity dictates, and then proceed out of the solar system like any natural object would. Researchers will collect their data, publish their findings, and eventually, the object will fade from our instruments, leaving behind a body of work that will inform future studies of interstellar visitors. Even this outcome would hold value. It would expand our understanding of how large interstellar bodies behave when heated by the sun, and how they respond to complex gravitational environments. Already, 3I Atlas has broadened our knowledge. It has shown that interstellar objects can be far more massive than earlier examples like Oumuamua or Borisov. It has revealed that compositions may differ sharply, with carbon dioxide playing a more significant role in this case. It has demonstrated that non-gravitational acceleration can appear in an interstellar comet that also shows active outgassing. These insights reshape our view of the material that drifts between star systems. In the coming years, observatories such as the Vera Rubin Observatory will survey the sky with a breadth and depth unmatched by previous facilities. Its wide field capability will allow it to discover faint, fast-moving interstellar objects that older surveys missed. Once those detections accumulate, we will learn whether 3I Atlas is a rare outlier or a representative example of a broader population. If its size, speed, and chemistry are unusual, we will know. If many future objects resemble it more closely than we anticipate, our models will adjust to reflect that. All of this leads to a larger question. Why does the possibility of artificial origin hold such a strong place in public discussion? Part of the reason is the long-standing curiosity about life elsewhere. For thousands of years, people have wondered whether we are alone. An object arriving from another star naturally triggers that curiosity. Even when the evidence points primarily toward natural explanations, there is also a scientific reason for the interest. 3I Atlas challenges expectations in several areas at once. Its trajectory has unusual features. Its chemistry differs from familiar comets. Its jet structures do not match simple illumination models. Its mass budget includes gaps that are not yet fully resolved. Any one of these anomalies might be explained by observational limits or incomplete modeling. Taken together, they form a set of questions that deserve careful attention. Science progresses by examining anomalies, not because they necessarily point toward the extraordinary, but because they often reveal gaps in our understanding. A puzzling result may turn out to be a calibration issue, a missing variable, or a physical process not yet included in the model. At other times, the puzzle signals something deeper, a new class of objects, a new interaction, or a behavior that requires rethinking assumptions. We do not yet know which category 3I Atlas occupies. What we do know is that the object is still under study. The data are incomplete. The models are being refined. We are early in the process of understanding something that has no close precedent. That lack of certainty is uncomfortable, but it is also a natural part of scientific work. 3I Atlas is now leaving the inner solar system, moving steadily away from the Sun and from the instruments that have observed it since July. Within a year, it will be far beyond the reach of detailed optical study, fading into a distant point of reflected sunlight. But the measurements gathered across these months will remain. The questions raised by its behavior will remain. The sense of inquiry it generated will remain. And somewhere in the direction of Sagittarius, other interstellar objects are likely drifting through the galaxy, waiting to cross paths with our telescopes and our questions. We will continue to watch, continue to measure, and continue to ask what these visitors can tell us about the wider universe and about ourselves.